Today in this series we will see the IC engine quick revision series. So in IC engine we make some assumptions in the air standard cycles, and these assumptions are that air is like an ideal gas. All the processes are going into closed system. Specific heat of the air is constant. All the processes are reversible processes, and no chemical change is taking place in the fuel. So this is the piston cylinder arrangement. This is the distance, stroke length, where piston move from this to this and reciprocate in this range. So this is stroke length, and this volume is stroke volume or swept volume. This is the clearance volume, where fluid is being compressed and finally is being combust. So the formula for this swept volume or stroke volume is very simple: area into length, pi by 4 d square into L. L is the stroke length, d is the diameter of the cylinder. V is the total volume, that is the clearance volume plus swept volume. So there is one term called compression ratio, is denoted by small r, is V1 by V2, or the total volume, this complete volume, Vc plus Vs, clearance volume plus swept volume, total volume divided by clearance volume. So say this is the state 1 and this is the state 2. So in stage 1 the volume V1 is यहाँ तक का सारा volume. So this is complete, Vc plus Vs, clearance volume plus swept volume. At stage 2 the volume is only this much, clearance volume. So generally in diagram it is written as V1 by V2. So this is V1 by V2, or V total divided by clearance volume. You can simplify, and one thing to remember is that this will be always greater than 1. Third point, for Otto cycle, these are PV and the TS diagram. 1 to 2 is isentropic process, isentropic or reversible adiabatic compression. 2 to 3 is constant volume heat addition. 3 to 4 is again isentropic expansion, and 4 to 1 is constant volume heat rejection. The same thing can be shown into TS diagram also, and the efficiency which we derive from the formula comes 1 minus T1 by T2, and this is 1 minus 1 divided by R. R is the compression ratio to the power gamma minus 1, and here gamma is the ratio of specific heat of constant pressure and constant volume. One thing to remember is that gamma is not always 1.4. Gamma is 1.4 only if we are considering air. So this is something we mistake sometime, and this is for efficiency. So from its formula of efficiency we can clearly see that if this factor R, which is the compression ratio, will be more, the efficiency will be more, because if this compression ratio will be more, this whole term will go down, will be less, and 1 minus something less. If this will be less, so this whole term will be more. This is what something shown into the graph, that as the compression ratio increases, efficiency also increases. At the same time, if gamma increases, ratio of the specific heat increases, again efficiency increases. But if we keep on increasing R, the efficiency will increase. Then we should say that we should keep compression ratio very high, but the limiting factor is called knocking, because in engine, if the compression ratio will be very high, then there are chances of knocking. So we cannot increase R endlessly. There is some limiting. So this is knocking is the limiting factor. Next is the diesel cycle. Again, the pressure volume diagram and temperature entropy diagram of both. 1 to 2 is isentropic compression. 2 to 3 is the heat addition but at constant pressure. 3 to 4 isentropic expansion. 4 to 1 constant volume heat rejection process. Same thing can be shown into the TS diagram. In TS diagram, if you remember, in the PV diagram, there was two processes, 4 to 1 and 3 to 2. Both were at constant volume, so these lines were having the same slope. But in this diagram, if we see that 2 to 3 is constant pressure process and 4 to 1 is constant volume. So when we will draw the TS diagram, the two lines 2 to 3, this 2 to 3 and 4 to 1, 4 to 1 are not of the constant slope, because this is at constant pressure, this is at constant volume. And we have to remember that the slope of the constant volume line will be more. If you remember, in thermodynamics we have seen this, that in the slope of this isentropic line is comes to be 1 by Cp and 1 by Cv. Okay, and Cp is always greater than Cv is small, so the slope will be more for the line of constant volume. Okay, this is basic thermodynamics, nothing more. So again, there are few terminology. This is cutoff ratio. This ratio, there was the heat addition in 2 to 3 at constant pressure, but at 3 we stop adding heat. So this is called cutoff. So this is cutoff ratio. This V3 divided by V2. Expansion ratio V4 divided by V3. Expansion is 3 to 4. So expansion ratio is V4 by V3. Generally, all the ratios are greater than 1. So we can simply say that if sometimes we confuse that whether this ratio was V3 by V4 or V4 by V3. So we can simply remember that generally all these ratios are more than 1. So ratio will be more divided by less. So V4 by V3. V3 also P3 by P2. V1 by V2 and something like this. Again, this is expansion ratio, and again the compression ratio. Compression ratio is V1 by V2. V1 is as equal to V4. So if you multiply these ratio, cutoff ratio and expansion ratio, we will get V1 by V2 only. Okay, and this is the formula for thermal efficiency. So this is not just the efficiency, this is the thermal efficiency of diesel engine or diesel cycle. Thermal efficiency of diesel cycle. So this is same as it was for the Otto cycle. 1 minus 1 divided by compression ratio to the power gamma minus 1. It is similar with additional term. Additional term is RC, which is the cutoff ratio to the power gamma minus 1 divided by RC minus 1 n into gamma. Okay, you have seen the derivation in your course. Next is the dual cycle. In dual cycle, we have both the constant volume heat addition as well as constant pressure heat addition. So this can be a very general term or very general derivation for both Otto and diesel. If we say make changes like V3 is equals to V4, okay, so this become Otto cycle. Or if we say V2 P2 equals to P3, so it will become diesel cycle. Again, some terminology for this. Compression ratio is same, V1 by V2. There is one more ratio called pressure ratio. Pressure ratio is P3 by P2. Okay, Cutoff ratio is same, V4 by V3. This is PV diagram, and similarly you can see diagram in TS also. Here also you can check and see that the slope of the line in the TS diagram, the slope of line with constant volume is more than line of constant pressure. Okay, so this is the derivation you have seen in the course, and this is the formula for its efficiency: 1 minus 1 upon r to the power gamma minus 1 into, this is alpha. Alpha is the pressure ratio. P3 divided by P2 into RC is the cutoff ratio, to the power gamma minus 1 divided by alpha minus 1 plus alpha into gamma into RC minus 1. You can check if alpha is 1, means this P2 equals to P3. If alpha is 1, so P2 equals to P3. If you put the value, it will come Diegel cycles formula. This will go on, this will go, this will go. RC to the power gamma minus 1 divided by gamma into RC minus 1. Similarly, if RC is equals to 1, RC is the cutoff ratio. So this will become V3 equals to will become V4. So this will be Otto cycle. If you put RC equals to 1, this term will go, this will be alpha minus 1, this cancel out, only this will remain, and this will be the efficiency of Otto cycle. Next is the comparison, that which cycle has more efficiency. These questions are being repeatedly asked in through exam. So first thing, if you have 2-3 options, you see and check that whether the dual efficiency of the dual cycle is in between or not. Okay, so efficiency of dual cycle will always be in between of Otto and Diesel. Okay, this is the first thing you have to check. On those options where the dual cycle's efficiency is not between of Otto and Diesel, those are in first go will be eliminated. Next come, okay, dual cycle is in between. Now in two situations, the efficiency of Otto cycle will be more than Diesel cycle, and those situations will be where the compression ratio is, it is written for same compression ratio, whether it is heat addition or heat rejection. If the compression ratio is same, then the efficiency will be more of the Otto cycle than the Diesel cycle. Okay, this is always. But we saw that efficiency of the Otto cycle was dependent on the compression ratio. So if we keep increasing the compression ratio, efficiency will be more. But due to more compression ratio, the problem was knocking was being observed into the engines. So that is why the second cycle came into the picture. So if we always say for the same compression ratio, okay, for same compression ratio, Otto cycle is more efficient. But these are not practical. These are not practical. That is why Diesel cycle came into picture, and for all other cases, the efficiency of Diesel cycle will be more than Otto cycle. And if in some time in question doesn't mention anything, so in generally agar it is being asked, so efficiency of Diesel engine is more than efficiency of Otto cycle. And generally you have seen that few cars in diesel give the better mileage than the petrol. So maybe this question is being asked in that context only. So if nothing is mentioned, then diesel efficiency is generally greater than Otto cycle. But if it is mentioned that for same constant, for same compression ratio, whether with heat addition or heat rejection, then Otto cycle will be more efficient. But this is not practical, this is only theoretical. Okay, but practical, what is practical? Practical are the limit, either the maximum temperature limit, material limit, maximum temperature, because engines or the cylinder pistons are being made from some material, and that material has some limit, either of the temperature limit, what maximum temperature that material can sustain, what maximum pressure that material can sustain, from which the cylinder or piston is being made. So these are the actually limiting factor or the practical factors. Same compression ratio is only in the theoretical case we see. Okay, so in this scenario where the limit is either maximum temperature or the maximum pressure, the efficiency will be more of the diesel cycle than the Otto cycle. Next is the equivalence ratio, or said by phi. What is equivalence ratio? This is the ratio of fuel to air. Here we have to see or be careful for one thing. In most of the IC engine, we always see the air to fuel ratio. You will see at many time I have written air to fuel ratio, air to fuel ratio, air to fuel ratio. But in the equivalence ratio, please be careful that here it is not air to fuel, it is fuel to air ratio actual divided by fuel to air ratio for stoichiometric condition. Stoichiometric mixture, stoichiometric mixture is where just combustion happen of the fuel, no excess fuel, no excess air, just required air for the given quantity of the fuel, no excess air, no excess fuel, neither lean mixture nor rich mixture. So if this equivalent ratio is equals to 1, then the mixture of the air and fuel will be called stoichiometric mixture. But if this equivalence ratio will be more than 1, so remember this is the fuel ratio, so it will be a richer mixture. But if this ratio is less than 1, then this will be lean mixture. This will be lean mixture. And for phi equals to 1, it will be stoichiometric mixture. Next is the minimum air required for the combustion of the fuel. Just combustion के लिए minimum air कितनी required है. So that is the stoichiometric ratio. But we give this in terms of air to fuel ratio. Air to fuel ratio. So if you remember in course we have seen this formula 8 into percentage of hydrogen into the fuel, percentage of carbon, percentage of sulfur, percentage of oxygen. This multiply into 100 by 23. Okay. Next is, see, we have seen that knocking is the problem. So to reduce the knocking phenomena in the SI engine, spark ignition engine, these are few factors which should be more. They should be high. So what are these factors? In the SI engine, these factors should be high. What are these? Self ignition temperature of the fuel. Self ignition temperature of the fuel should be high. The engine speed should be high. The turbulence inside the cylinder should be high. The octane rating should be high. In which, remember, we are seeing spark ignition engine only. So if these conditions are high, it will reduce the knocking. There are few conditions which should be low. Like the compression ratio should be low. As I have already told, compression ratio was the limiting factor. That is why diesel engines came into picture. So compression ratio is low. Inlet temperature should be low. In, remember, spark ignition, petrol engines, inlet temperature, inlet pressure, this should be low. That is why we generally do not use the supercharger in the petrol engines, because that will increase the pressure or the temperature and in a way will increase the knocking tendency. Engine speed should be limited, and the flame travel distance we have seen into the course, this should be low. And there are few things like supercharging and a spark advance, they should not be even low, they should be totally absent. Otherwise knocking tendency in the petrol cycle or petrol engines will be very high. In the similar way, if you see the compression ignition engine, or in a way we can say diesel engines, for reducing the knocking, the compression, these should be high, the compression ratio should be high. Inlet temperature, inlet pressure, this should be high. That is why we use the supercharger or turbocharger in diesel engine, and there that is efficient. Because if this temperature will be high, inlet temperature, inlet pressure will be high, that will improve the efficiency as well as the knocking tendency will be reduced. Combustion chamber temperature, if it is high, no problem. And the cetane rating. In the similar way, in SI engine it was the octane rating, so here it is the C10 rating. There are few things we should be low, like self-ignition temperature should be low. That should be low. But if you remember in SI engine, the self-ignition temperature of the fuel should be high. Okay. Delay period should be low. RPM should be low. That is why you have seen most of the diesel engines are like slow engine. Like they are more powerful, but slow. Like we are making the trains or trucks, more powerful, but RPM are less. At high RPM, we have the cars also, but at higher RPM, if we have the same size of engine, then the knocking tendency will increase. Okay, so RPM should be low. Engine size again, and these thing in injection angle advance, this should not be present. If the injection angle will be advanced, or you say, if you remember in CI engine we inject the fuel, if we are injecting the fuel before the time, that will increase again the tendency of the knocking. And supercharging, yes, here it is welcome. Why? Because if there will be supercharging, the inlet temperature and the pressure will be high, and that is the desirable factor. The high temperature and inlet temperature and pressure is the desirable factor for reducing the knocking. So that is good for us. So that is why in diesel engine or the CI engine, supercharging is good. But in SI engine or the petrol engine, we say no to supercharging. Say no to supercharging because that will increase the chances of knocking. Now these are the few simple formulas like air fuel ratio by the simple carburetor. This is the mass flow rate of the actual air divided by mass flow rate of the actual fuel. And you have seen into the course that these were the formulas. I'm just showing the formula and telling you the terms. Like this is the discharge coefficient of the air, this is the discharge coefficient of the fuel, this is P1 the inlet air pressure, A2 area. A2 I'm saying, if you remember, this is the carburetor, this is the simple carburetor. So this is the air coming from this side, air coming from this side, this is fuel into the tank, this is the venturi. In venturi at this level the volume the pressure will be very low, and due to the low pressure the fuel will move into this channel in this path, and the fuel will come here and air from coming from here, and air and fuel will mix and the mixture will be delivered to the cylinder. So this is the simple carburetor. Air is coming, due to venturi there will be high velocity but low pressure. There will be high velocity but low pressure, and due to the low pressure the fuel will come from here to here, and the air and fuel will mix and will go to the cylinder. Okay, so this is the area A2, this is the throat area here, and this is the inlet air coming A1. This is what I'm using in the formulas. So this is A2 R as constant, T1 is the temperature, into 2 Cp constant pressure specific heat, P2 by P1 to the power 2 by gamma minus P2 by P1 to the power gamma plus 1 by gamma, divided by CDF discharge coefficient of the fluid nozzle, AF area of the fluid nozzle, this was the nozzle, so this area is AF, this is the AF area, into under root of twice rho F density of the fluid into P1 minus P2 minus rho F into GZ. This is the case when the air is being considered as compressible, as it is, air is always compressible. But if we have some assumptions given like consider air as uncompressible, so these pressure terms will come in this way. And generally for higher discharge, this P1 minus P2, the pressure difference is very high compared to this Z term. Z is this fuel level height. So this height from the tank level to the discharge level is Z. So this pressure difference from P1 to P2 is very high compared to head of this Z. So generally we neglect neglect this term, if we neglect this term, the P1 P2 P1 minus P2 term will cancel out, and this will be simply like this. This is mostly used formula CDA, the discharge coefficient of the air, the discharge coefficient of the fuel nozzle into A2, the throat area, AF, the area of the fuel nozzle, into density ratio of air to fuel. As it is air to fuel ratio, here also upper side will be the density of air and lower will be density of fuel. Okay, next is, this is just data to remember. Sometimes it is being asked to the exams, like air to fuel ratio requirement in different conditions are suppose idling, so air to fuel ratio is like 12 to 12.5. In normal cruising condition it is 16 to 16.5. It is higher, but it means that we need less fuel in this range, more air, because ratio is air to fuel. So 16 to 16.5 मतलब lean mixture. So 16 to 16.5. Power, maximum power range, the air fuel ratio is 12 to 13, and in transient operation or like starting, it is need very rich mixture. If you have seen in the winter, if the vehicle is not starting, we uh, use the choke, you know what we do when we use the choke, we make the rich mixture. This is 3:5. The value is less, but it is rich. Why? Because ratio is air to fuel, not fuel to air. So this low value indicated the rich mixture. So in a starting, we need very rich mixture, and in normal or cruising condition, we need very lean mixture. Okay. Next is the fuel injection volume. These are the simple fluid mechanics formula: CD, discharge coefficient, into area, velocity and time. Velocity twice pressure difference divided by density of the fluid, and the time of injection, this is time of one injection, this is some time asked. The theta, see, it is engine is rotating complete cycle, but the injection is not in the complete cycle. There are suppose the 4 steps or 4 strokes, so injection is only in this period. There is a fuel injection, then the fuel will be compressed, then the fuel will be combust, burn hoga, then expansion hoga. Okay, so we are considering the time of injection, so angle of injection only. So this will be theta, this will be theta, divided by 6 into n. N is the number of rpm at which engine is rotating. Now next are few like indicated power. So indicated power is PM L into LAN into K divided by 60. PM is the mean effective pressure, L is the stroke length, A is the area, N is the number of rpm, and K is number of cylinders. Suppose one engine has the 3-cylinder engine, so K is 3. If one engine has the 4-cylinder engine, so K is 4. This is for 2-stroke engines. If it is a 4-stroke engine, the indicated power will be half. So instead of 60, here will be 120, rest will be the same. Brake power, in college, if you remember, there was an experiment where we need to find out the brake power. If you remember in college lab, what we used to do, we need to we measure this torque only. Okay, there was an arrangement. With the help of that arrangement, we measured the torque, and using this formula we told that this is the brake power. If you remember, in college we have done this experiment. We measure the torque and then calculate. Torque is being measured and brake power was being calculated with the help of this formula. So this is 2 pi n t by 60. And what is the frictional power? Ideal minus actual. This is the actual actually. So this is ideal. So ideal, what is the difference of both is where this difference is being lost into the friction. So this is the friction power, indicated power minus brake power. Okay, and what is the mechanical efficiency? Mechanical efficiency is what is output divided by input. Output, what we are getting is brake power. Input, what engine is producing, is indicated power. So ratio is mechanical efficiency. In a similar way, there is a volumetric efficiency, the actual volume of the air or mass of the air divided by alpha A, rho A, density of the air, into Vd, the discharge velocity. Similarly, thermal efficiency, indicated power divided by fuel consumption rate, mass flow rate of the fuel into calorific value of the fuel. In the similar way, this is the indicated thermal efficiency. There is another brake thermal efficiency. Instead of indicated power, here it will be brake power. So brake power divided by mass fuel consumption rate into calorific value. If you see, the mechanical efficiency is the ratio of the both. So sometimes this is asked into the question without giving indicated power and brake power. So if the efficiencies are given, this is just the ratio. Similarly, the indicated specific fuel consumption, or similarly brake specific fuel consumption. This is nothing that mass of the fluid required for the given amount of indicated power. So this is just the ratio. Here it is the ratio of mass of fuel to the brake power. Okay. Next is the mean effective pressure. If you remember, in the indicated power we use the term mean effective pressure, PM. So how this mean effective pressure is calculated? Very interesting. If you have seen into the course, we have derived one formula for the to calculate this mean effective pressure. So to calculate this mean effective pressure, there is one instrument is being used. With the help of that instrument drew some diagram like this. This is called indicator diagram. This diagram has certain area, say A, area of diagram. This diagram has certain length from this corner to this corner, LD, length of the diagram, area of the diagram. Since this is P versus V diagram, so this comes the mean effective pressure comes area of diagram divided by length of diagram. Simple, very simple. If you see, this is the area divided by length, what will come? The pressure. Now what is K? K is the spring constant. Okay, derivation you have seen, it is just as simple as it is. So mean effective pressure is spring constant into diagram area divided by diagram length. Okay. Now, next is the fuel constituents. See, whatever fuel we are using, be it diesel or petrol. So these fuels are hydrocarbon, either in the form of a straight chain or in the form of cycle. If the fuel is in straight chain form, that chain might be saturated or unsaturated. If that chain is saturated, these fuels are paraffins. If the single straight chain is unsaturated hydrocarbon, then these fuels are olefins. But if these fuels are not in chain form, these are cyclic. Cyclic can also be again saturated or unsaturated. So if this cyclic and saturated, these are naphthalenes, and cyclic and unsaturated, these are aromatics. So this is just the information. Now, next is the octane number. This is important. This is the octane number. So what is octane number? See, we have seen that in petrol engine or SI engine, high octane rating should be good for us because knocking will be less. So if the octane number is 80, what does it mean? If octane number is 80, what does it mean? Octane number 80 means that if the fuel, suppose we are using one fuel or petrol, and we have got tested this fuel and got the octane number of 80. Okay, so what is the significance of this 80? This number, what is the significance of this number? So now significance is that the fuel we are using is equivalent to the fuel which is a mixture of isooctane and N-heptane, and in this mixture the isooctane is 80% and N-heptane is 20%. Okay, so if we take a mixture in which the isooctane is 80% and N-heptane is just 20%. The octane rating of this fuel will be 80, and the fuel which we are using in our engine is equivalent to the quality of this fuel. So this is the significance of this octane number. In the to, this is desirable for us, as we have seen the octane number should be high in SI engines. So this is desirable to have higher octane number, and to increase the octane number, to get the higher octane number, tetraethyl lead, this used to tetraethyl lead used to be mixed into these fuels, but due to some environmental problems this is being banned by the governments, and currently this is not being used. But when we were using this tetraethyl lead, this used to cause the problem of the spark plug falling, and to avoid that falling we used to add on those times ethylene dibromide, but now this is totally banned, so we have no option of adding TEL to increase the octane number. In the similar way is the cetane number. Cetane is C16H34, C16H34. This is the cetane. So once again, what is the significance of the cetane number? Suppose the cetane number is 85. Cetane number is 85 of my fuel. So significance of this number is that the fuel of which cetane number is 85 is equivalent to the mixture of 85% cetane and 15% अल्फा मिथाइल नेफ्थेलिन. इस मिक्सचर के इक्विवेलेंट है वो फ्यूल जिसका सीटेन नंबर 85 है. There is also one formula which have the relation between cetane number and octane number. The cetane number is 60 minus octane number ka half of octane number. So this is sometimes used, and with the help of this formula you can clearly see if the octane number will be high, the cetane number will be low. So if we use a fuel of high octane number, so its cetane number will be less. That is why we say, what if we put the diesel into the petrol engine, or what if we put petrol into the diesel engine? So what will happen if we put the petrol into the diesel engine? For petrol the octane number is high, so for petrol the cetane number will be very low, and for petrol cetane number is low, and if we use that petrol into the diesel engine or the compression ignition engine, if we use, the cetane number will be cetane number will be low, and due to the low cetane number there will be chances of knocking. Why? Because we need high cetane rating, high cetane number is required. So if we, with the help of this formula, we can see, you can see कि अगर पेट्रोल इंजन में हम डीजल डाल दें तो उसकी जो रिक्वायर्ड रेटिंग है नॉकिंग के लिए वो गड़बड़ा जाएगी. So there will be chances of knocking. There are two basic, this formula of the fuel sensitivity is rated research octane number minus motor octane number, or anti-knocking index is research octane number or motor octane number average add करके divide by 2. There are two simple thing of the pollution level. In petrol, the pollution, carbon monoxide and hydrocarbon pollution level will be higher in the petrol engine, but the NOx, odor and smoke, this will be higher in diesel engines than petrol engine. This is one information. Second is the pollution level versus air to fuel ratio. So if we see the air to fuel ratio in the range of 14 to 60 is good. Why? Because the pollution level of the hydrocarbon will be minimum in this range. Carbon monoxide will also go down as the air fuel ratio will increase. Why? Because the fuel will be, then you will see, will be more leaner. If fuel will be more leaner, the carbon monoxide pollution level will be low, but again we have certain limit. We cannot increase the air fuel ratio endlessly, otherwise engine will stop working. So we have to make trade-off. And if you see the NOx, this is highest in this range. Similarly, the pollution level versus speed, if you see the NOx has no effect, but the hydrocarbon and carbon monoxide will go decreasing as the speed increases. So this was just additional information. This is all. If you want to take a screenshot in one go, so you can take. This was whole IC engine. All the best for everyone, and thank you very much for those who are watching. Thank you very much.